Hi everyone, it is my pleasure to give a keynote speech in CSIE 2022 and the CIEDH 2022. I would like to appreciate the Professor Luo's invitation and also the support by Fuji and support by Zhenfu. Today, I would like to discuss some of my research outcome about the assisted intelligence in Taiwan's semiconductor manufacturing practice. I am Morris Fan and now serve as the convener of IEM program, the Minister of Science and Technology, and I'm the professor of Taipei Tech, Taiwan. Also serve as the editor-in-chief of Engineering Optimization, published by Taylor and Francis. So this is the outline of my speech today. I will give you a very quick review and a broad idea about artificial intelligence, machine learning, and deep learning. Then we define what is called the assisted intelligence. Then I would like to present some of my study, and this is a case study of the AI in semiconductor manufacturing. So the research material is based upon a paper that's already published in the year 2020 and published in the semiconductor, now in the IEEE transaction on automation science and engineering. Then later, if time is allowed, I will briefly mention what is related AI works in semiconductor manufacturing. Then I expect some question and comments. So artificial intelligence, as you understand, and is an area of the computer science that emphasizes the creation of intelligent machines that mimic the behavior of the human beings. Then we like to perform some prediction, perform some classification, or some transformation. So basically, up to now, there are three major disciplines: the deep learning, machine learning, and artificial intelligence. So we understand deep learning is a subset of machine learning, and machine learning a subset of the artificial intelligence. So machine learning is considered a method of data analysis that can automate analytic model building using algorithms that iteratively learn from data. So based upon the data, we learn the feature. Based on the feature, we build a model based we call the machine learning model. So how we experience machine learning during our daily life, like website recommending items, and the speech and the face recognition, such as so when we to take a flight, and then we should go to the immigration gate and the security check and the customs. And the government agencies such as the public safety, and in our community, so they equipped with the CCTV cameras and smart traffic flow solution like ETC and social politics. Then in financial engineering or fintech, the banks and other business in financial industry for two key purposes, such as ATM services and prevent the tax fraud or money laundering. So basically, machine learning method can be classified into two different categories. First one, the supervised learning. So the algorithms are trained using the label data, using the human annotations, such as input where the desired output is already known. And then the other type, on the contrary, is used against the data that has no historical label. So I think that would be the most of the cases, which will be more realistic. So the system is not told the right answer beforehand. So the algorithm must figure out what is being shown, and the goal is to explore the data, find some structure within the data. So in between, there's another learning in between. Is called the semi-supervised learning. It's used for the same application as the supervised learning, things like so. It's also known as a future learning, but it uses the both label and unlabeled data at the same time for training. So we like to use a very limited number of annotated data. Then we try to provide the automatic labeling techniques to label a greater amount of unlabeled data. So like a web page classification. And then in the most of the case, when we just are browsing the web pages, the most of the web pages are not classified or provided with the annotation. Then one of the most innovative methodology in machine learning that will be the reinforced learning. With reinforced learning, things which can adapt with the evolving changes through the environment. So algorithm discovered through the trial and error, and which action is the greatest reward. So most of the reinforced learning is initially designed with the gaming and robotics. So really got a really a big improvement. So it involved initially with the DeepQ network, the policy gradient, deterministic policy gradient. In 2017, OpenAI just launched a new idea. So we would like to transform from the on policy into off policy. So the Google and the OpenAI, they do the joint research to propose another different approach that called the PPO, the proximal policy optimization, by using the trust region optimization. So algorithm group by learning style: supervised learning, unsupervised learning, and the reinforced learning. I think in the future, from narrow AI to the universal, more universal AI application, I think that will quickly tackle the reinforced learning, since that will be the mainstream of the artificial intelligence nowadays. So machine learning algorithms are categorized by the level of assistance from human beings they got from the humans, so how they change over time. So let's look at the most, I think the most motivating example. So I always use this a PowerPoint slide in my class. So the learning like sorting Legos. So simple example of a child sorting Lego blocks illustrate the difference between the different learning. Like we have a supervised learning, children has to sort the color blocks in terms of the color and shape. Then from supervised learning and evolve into the unsupervised learning, the children have to sort the block by themselves. They figured out what is the color, what is shape, or both, without any instruction from parents. And then evolving into the reinforced learning, then there's a tutor we call mommy or father. The children get feedback from mom, and when they do something right, they give the candy, or something wrong, they will be taught over and over again. So I think it is a quite motivating example about the difference of the learning. Then about the assisted intelligence, so there's this intelligent lens to classify the AI into 4 different categories. So look at the horizontal axis. There's a human in the loop or no human in the loop. And for the vertical axis, there's a hardwire specific system, adaptive system. Now today, we address most of the problem within the assisted intelligence. That means the AI system that assists a human in making decision or taking action for this is about 60 or 70% of their job. And then there's a hardwire system designed by human and put their idea, put their algorithm or the rule into the artificial intelligence. Then that do not learn from the interaction with human beings. So we call the hardware specific system. So it's also called assisted intelligence. So for the remaining 30%, if trouble comes about, then the human intervene and try to help to perform the troubleshooting. So learning from different type of data, so a resource of the unstructured data is fueling the rise of machine learning to understand the data better. So for example, sensor data, which consists of the signal detection, alarm monitoring, or for the purpose of the PDM, predictive maintenance. And for the video search, pattern recognition, the motion tracking, for image, the facial recognition, object classification. And another really hot topic is NLP, natural language processing, including the application in the social media like a sentimental analysis and the customer service analysis and so on and so forth. So data lens, many types of data can be used, develop, and train the AI based upon the structure or the complexity. They can be classified into 3 types: the structure, the information with a fixed length or fixed data format or schema, typically stored in the tabular format, like 30 years ago we learned the ER model or EER model, the relational database, and a semi-structure, the label and structured data like JSON, extendable market language, and the unstructured. So we have it every day in our daily lives, like a raw text, image, audio, video, and sensors data. So for the technology lens, so AI layer, we have a sensory layer, how we get the data, what is the source of the data, behavior layer, going to deploy in the translation or the deep question answering and the robotic processing automation. And in the cognitive layer, like we use a different learning method and the algorithm, machine learning, deep learning, reasoning, and scheduling. And finally, this is our backbone in the algorithmic development, like statistic, econometrics, optimization. So the machine learning takes the raw data to learn the feature, make up the model of the real world. So first of all, we learn the feature from the data, and we build the model. Typically in machine learning, we are model centric, and recently the Andrew also proposed we like to build a model based upon the quality of the data. That is called the data centric model. Okay, this is the case we like to address, assisted intelligence, and this is already published in the 2020. And like last year. So the title of the paper is a data-driven approach for fault detection and the diagnostic in semiconductor manufacturing. The major objective, how to detect, how to identify key parameter and the key processing step in the semiconductor manufacturing. So the data, the real data set was collected from the global well-known fabrication semiconductor plant in Taiwan. So it is a thin film data set. The plasma enhanced chemical vapor deposition is known as a CVD. So this process consists of two chambers, chamber A and chamber B. So both data are investigated in this study. The sample are totally imbalanced, so only very limited number of the bed wafer. However, we have a really large number of the good wafers. So each wafer records different finish time. So in this case, in this data, we have 66 SVIDs. So SVID stands for the parameter or the status variable identification. So during the stage of the preprocessing, we disregard the 7 SVID since among 66. The 7 SVID are more qualitative. There's nothing to do with the quality of at least fault detection and classification tasks. So this is an illustration for the wafer. So you can see that for different wafer, they have a finishing time. So for the wafer one, it is a good wafer. For that wafer, we collect a 310 measurement. However, for wafer 2, we collect the 312 measurements. So for each wafer, they are inconsistent. So before we can perform the data science, data analytics, we need to perform the data preprocessing. So the framework of the research, first of all, we like to calculate the variant importance. And then the second step, we're going to identify what is the key step. Then based upon the key parameter identification, a key step identification, then we like to use most of the wafer data and perform the wafer classification for the further verification and validation. Finally, we perform the data visualization. Okay, key parameter identification. So we define the label. It is a good or bad on time series temporal row trace data. For example, we told you we have 58 SVID. For each SVID is a matrix. So since we have a number of the wafer, for example, a normal wafer, they have the finish time. We have a 350.3 seconds for the first wafer, and the bed wafer we have a 370.7 seconds for the bed wafer. So need to do the time synchronization into the interpolation. So okay, so for each SVID, there's a data matrix. Totally, there's a data cube. So key parameter identification, we adopt the random forest, which was developed by the Leo Bryman in the 2001 from the UC Berkeley, which is a wrapper method for feature selection. So the trace data need to be normalized or standardized beforehand, since random forest is aggregation-based classification or CART. So in which case the gene importance is used for the criteria how we spread the node. This is 1,000 trees are considered maximum depths. We do the pruning of the tree. Maximum depth is 7, and maximum feature select out of 59, so take 8. So we got the in terms of the gene importance, we calculate the importance rate of each parameter for HVID. So we just leave the feature importance in this plotting. So the red line represents chamber A. The blue line represents the chamber B. So you can see there's something interesting happen here. Between the 25 or 32 around. So the higher importance exhibit. That means we might consider between the 25 and 32. They can be considered the key parameter with higher importance, and they have a higher the higher importance rate. So we'd like to identify key parameter in terms of the automated clustering. So we set up k equal to 2 in k means to separate what is the key and the non-key. The left-hand side is for the chamber A, right-hand side is chamber B. Then, so for the chamber A, we had 16 key parameter SVID are identified. Chamber B, we identify 17. In commons, totally, we identify 16. Totally, so we select certain key parameters. However, then 8 out of 13 are confirmed by engineer's domain. All key parameters are found. So you can see from the SVID 25 to the SVID 32. There's one more information I would like to share with you. Since even though from 25 to 32 are confirmed by the process engineer, however, we find one additional key parameter which never aware of by the process engineer. That's SVID 12. Later, they perform the confirmation experiment. They confirm the SVID 12 is not important. However, they never pay attention to that. So based upon the results, so we identify at least a key parameter. Then we like to further identify. Based upon the result of the key parameter identification, can you identify further the key processing time? Then this is a key step. This is intervals of the processing time defined by the process engineering beforehand as well. And this is chamber A. They define chamber A in they just dissect. They just decompose the 350 times into the 15 different steps. They have different intervals for chamber A and chamber B as well. So you can see that they have a different finish time. Then key step label identification. Now we transport the data cube. Since at this stage, the feature we feel interest in going to be the time. So the time going to be the feature in comparison to the previous stage, the key parameter identification, that SVID going to be a feature. In this stage, the time processing time will be considered as a feature to be screened out. So for each SVID, there's a data matrix like this. So it's put based upon the different good wafer and bad wafer. So what is the key processing time? They can separate good wafer and the bad wafer most. Then with higher importance, that will be considered the key processing time. So we have a totally there are 59 matrix to be dealt with. Then this is the results. Can be seen from the chamber A and chamber B. You can see that between the 180 to 200 second for chamber A and chamber B. This they indicate there's a high importance for this interval. So which can map to here. This is step number 7. This for the chamber A. So we're going to map to the original temporal profile data. This around here. So yeah, see, the red line represents the bad wafer, the blue line represents the good wafer. This is very difficult to spot for the process engineering to differentiate good wafer and bad wafer. And also for chamber B, between the time 20 to 80 around, you can see that this interval has been identified with higher importance. So that is corresponding to that. This illustration of the SVID28 has been also identified as a key SVID as well. So based upon the SVID, there's a key parameter and the key processing time going to between the 20 second and 80 seconds. So now the key processing time and key parameter have already been identified. So we'd like to see, is that possible to transform those research outcome into data visualization now? So we like to take advantage of the TSNE. So data visualization. So first of all, the TSNE performed the dimensionality reduction. So visualize the multivariate. So since we have 9 different SVIDs, then we're going to reduce the higher dimension in the 2-dimensional space. Since there's a 9 SVID considered key, then for each SVID for chamber A, it contains 315 seconds. For the chamber B, the 9 key SVID are considered as well. However, in chamber B, there are 309 seconds are measured. So for TSNE, so for the chamber A and chamber B, the TSNE plot are plotted separately. So in TSNE, we use a practically 30 exaggeration for the learning rate, 500, and iteration 1000 for illustration. So you can see that we're going to also, the result of TSNE also compared to PCA, this chamber A and chamber B. From here, we can see that the TSNE can separate the good wafer and bad wafer more significantly than PCA. You can see that for chamber A. This is very difficult for PCA to differentiate. The red dots represent the bad wafer, the blue ones represent the good wafer. Okay, then, so can do the mapping, for those SVID can be found. Okay, so there's the corresponding to the step 7 going to be the key, and for the SVID28 and for the key processing time, it's between the 180 and the 200 second. Okay, for the remaining 5 minutes, I would like to mention some of my research. So since time is very limited, if you feel interested, I think the PowerPoint slide is available upon request. Present your query to Professor Luo, and I think Professor Luo would like to disseminate for the academic purposes. So this is published in 2019. This paper was done. The purpose of this paper is to identify key parameter identification by using the image processing technique. Particularly, we use a Fourier transform. And this already published in the 2021, the published IEEE transaction on automation science engineering. That paper addresses run-to-run control. However, there's more than 2 products going through the same tool. So high mix product production run-to-run. So we developed a new double EWMA run-to-run control using the disturbance accumulating strategy. We compared the existing methodology in literature at the improvement rate, most of the case over 50%. Then there's another problem I addressed recently. This is only an early view, accepted also online already in the IEEE transaction on automation, science, and technology as well. We resolved the back-end of line problem. However, the problem can be traced back to the pipeline in the front end of line. So this problem has not been solved in the literature and in the practice. So in this case, we propose a logistic regression-based approach. Then try to identify the problem happening in the backend. However, how can you trace back to the pipeline the root cause finding in the front end? So there's another paper. The paper I address the product to product, between product, the transfer learning and virtual metrology. However, this is a different in a different industry. I address this virtual metrology problem in the TFT LCD industry, and we use the transfer learning from the base model to the new product model. And another paper, this is an image-based paper that's already published in IEEE transaction and instrumentation and measurement in last year. So we use a cycle game. So we performed automatic defect detection without using manual annotation. With a very limited number of the defect image of the semiconductor manufacturing, particular the surface of wafer. Very limited. I use a cycle game. Without the manual annotation, we can directly detect what is the defect type and location on the surface of the wafer. That's quite good, quite effective. And this is another early view paper, also accepted by the IEEE transaction on automation, science, and engineering. We address the key feature identification for anomaly detection using the SOM, self-organizing map, and the ADA boosting. So this problem thinks we like to differentiate the quality level of the good wafer in the routine manufacturing practice. And the last one just accepted until the end of the last year. So in this paper, we try to provide the more add-on to the current FDC methodology in semiconductor manufacturing, which address the data visualization process anomaly detection using the online t-SNE. So we try to just connect all the data point through the t-SNE map, then perform the online t-SNE. They provide the data visualization aid to the process engineering to facilitate the fault detection and classification routine work. So, okay, that. Okay, thanks for your listening. I think I spent around 33 minutes for my speech. So I expecting some comments and some feedbacks and a question. Thanks for your listening.